So today we're going to finish faster exponential time algorithms, or small space. Specifically, we're going to do inclusion-exclusion. I just want to say a few more words about that. Slash zeta transform and Mobius inversion. And then the remainder of the class, as well as next lecture, I'll tell you some things about, well, an area I work in, which is streaming and sketching. Okay, so let's get started. So I just want to write something I wrote on the board last time, which is, this is a fact. We proved it last time. This was inclusion-exclusion, which said that for all sets R subset T, we have that the sum over all S's that are sandwiched in between of -1 to the T minus S is equal to R equals T. Okay? Remember, this is just one. Whenever I put a Boolean expression in brackets, it means 1 if it's true and 0 otherwise. And we defined the zeta transform. So if we have a function f mapping sets into some ring, we defined f hat, this is the zeta transform of S, was the sum over all R subset equal to S of f of R. And last time, what did we say? We said last time we ended with K coloring. Oh, we have a scribe today, I think? Yeah, okay, great. We said let f of x, let f of, let's say, S be an indicator for S is a non-empty independent set in our graph. And then we had this claim which stated that K, the graph G is K colorable if and only if, let's say, the sum over all S subset equal to V, -1 to the n minus S. This is just, if you want to say this differently, this is just the size of V minus S of, let's say, f hat to the K. Is bigger than 0. Okay. So I mentioned at the end of last lecture that this will let us do things more efficiently, and I also mentioned that you can prove this claim using inclusion-exclusion. So the scribe actually put the details of why this claim is true in the notes. I am going to show you a proof of this claim, but I'm actually going to show it to you as basically just one example of something more general. Okay. So, first of all, how would someone come up with this formula. Right? It's one thing to just show you something and then have you prove it, but it's harder to come up with such things, right? And I'm going to show you that the way that you would come up with this is basically via this zeta transform Mobius inversion, which well, I guess I defined the zeta transform, but I will define this thing here is called, so the zeta transform, this f hat. And let me just include some references. So first of all, this thing here, we're going to see soon. You can compute it in either O star of 3 to the n time and Pauli n space, or you can do it in O star 2 to the n time n space. Okay. And these are due to independent works. One is Bjorklund and Husfeldt. This is Fox 06. And the other one is Covisto. I'm probably saying the name wrong. Fox 06. And actually, the former, the first of the two papers, I mean, these were two independent papers. They were published at the same time. But the first paper, this one, can also get something like O star of 2 to the 2.461. Well, O of 2 to the 2.2461 to the n time, and Pauli n space. And it's actually an open problem. It's an open problem to get 2 to the n time, or roughly 2 to the n time, with Pauli space. Yeah. Okay. So rather than prove that claim and talk about running time specifically for K colorability, I want to show you why this is just a kind of falls out of something more general. Okay, so we have F as before, meaning I said F maps sets to some ring. And I defined the zeta transform. That was the F hat. And then I also defined the Mobius inversion formula. And I'll call that F tilde. F tilde of S is the sum R subset of S, -1 to the size of S minus R, F of R. Okay. And kind of the real place where this formula comes from and why it works is the following. Claim F hat tilde equals F tilde hat equals F. Okay. Is it clear what I mean? If you take the zeta transform, then Mobius invert it, you get F. And if you do it the other way, if you first do the Mobius inversion and then do the zeta transform, you also get F. Okay, so let's prove this. And I want to show you just one of the directions. The other direction is very similar. We'll show that if you zeta transform the Mobius inversion, you'll get F. Okay. In the other direction. Well, not the other direction, but showing that F hat tilde is F is similar. So let's evaluate this thing on some set. So we have, let's look at F tilde hat of T. Okay. So good. So what does it mean to take F tilde? So we're taking the hat of the tilde. Let's see. So, well, first, let's just look at what is F tilde of T. F tilde of T is equal to the sum of S subset equal to T, negative 1 to the T minus S of F of S. Okay. Which implies that F tilde hat of T is let me see, where is my definition? The sum over, that's the sum over, let's call it S subset T of, now I'm confusing myself with double indices. Okay, so of F tilde of S right, which is equal to, so let me actually call this F tilde of S. So this is now R as a subset of S. And this thing is equal to the sum of R as a subset of S as a subset of T, negative 1 to the S minus R, of F of R. I don't know how I... I feel like I'm off by a minus sign somewhere, but let me continue. Seems right. Okay, good. And now I want to invoke inclusion-exclusion at some point. So this is equal to sum over R subset equal to T, and then F of R, and then sum over S, and then S is R is a subset of S, subset of T, negative 1 to the S minus R. And what I wanted to say is that the thing that's confusing me, I wanted to say that this thing, I seem to have confused myself, hopefully is going to be r equals t, in which case I would just be left with f of r. I'm sorry?
If you get from there to the summation, you divide with two sums and exchange the order, then you get exclusion, meaning you don't need to write with the triple index.
The problem is I really wanted this to be t minus s, not s minus r.
If you plug there before rendering for the third, for the second there, you write the above and you just exchange the sums and you pull f of r outside and you get something like inclusion exclusion side. Exactly. I think. Meaning you write of f of tilde is before, you exchange the sums, you get the far outside.
Right, so I think.
So this equals exactly s equals r. Bracket s equals something like that.
Okay, so I'm not sure I followed exactly that, but I think this thing is equal. I think this thing is going to be equal to -1 to the t minus s times some fixed sign, right? Which doesn't depend on anything else. In which case, this thing dies when r is not equal to s anyway, so this sign doesn't matter, and otherwise you're only left with one thing in the summation anyway. Okay. So I think I confused myself by being off by this sign, but I'll fix this at some point. But I'm pretty sure what I said is okay. So, okay, good. So given that this is true, where did this formula come from for k colorability? Okay. So okay. Good. So let's define a function which is number of ways to write S as the union of k non-empty independent sets. Okay. So if G, so we really want to know, so G of t being bigger than 0 is the same thing as saying k colorable. T is really the set of all vertices. Right? What does it mean to be k colorable? It means we can write our graph as a union of k independent sets, non-empty independent sets. Of course, I didn't say anything about these being disjoint. Okay. But that doesn't matter. If you can write it as a union of k non-empty independent sets and they overlap, okay, I mean, just greedily go through one by one and assign it the first color that of the set it was in. If it's in another set later, just ignore it the second time around. Okay? Basically, all I'm saying is, if you can write it as a set of possibly overlapping independent sets, as a union of possibly overlapping independent sets, you can also write it as disjoint union of independent sets. Just drop, if a vertex appears in multiple sets, drop it from all of them except one. Yep. Okay. So we just need to be able to compute G of V. Okay. But the claim is that, well, not really, it's not really even at the level of a claim. Just note that G hat of S is the same thing as F of hat of S to the K. Okay. So what is F, remember? F just is an indicator function for non-empty independent sets. Okay. So I claim that the way to see that these two things are equal is just to interpret what they both mean in words. So what is this? So G of S is we want to write S as a union of K non-empty independent sets. So what does G hat of S mean? Under the definition of the zeta transform, that means we want to count the number of ways of coming up with unions of independent sets such that the union lies in S. It's contained in S. Okay. So we want to choose K independent sets that are all K non-empty independent sets that are all contained in S. That's what this is counting. How many ways are there of doing that? Well, how many ways of doing that are there? Well, just choose K non-empty independent sets, or just count how many non-empty independent sets are contained in S and raise it to the kth power, which is exactly the right-hand side. Okay. Does that make sense? Are people okay, or are people confused? Okay, I'll interpret that as people understand what I'm saying. So let's call this double star. Both left-hand side and right-hand side of double star count the number of ways of choosing K non-empty independent sets that all lie in are contained in S. Okay. I'm sorry?
Are they ordered?
Yeah, they're
Because taking the K, you need to be ordered.
right. So they're ordered. So if you take set 1 and then set 2 versus set 2 then set 1, those count as two different things for them to be equal. That's right. So that implies that G of V, which is the thing we want to compute, G of V is equal to, by Mobius inversion, it's equal to G hat tilde of V. And we just said that G hat is this thing. So that's equal to F hat of S to the K tilde. Or I guess I should write it as F hat to the K tilde evaluated at V. Okay. So that's where that formula I wrote before is coming from. It's just taking F hat and then taking the kth power and then Mobius inverting it. So claim we can compute say, all F hat S or F tilde S values sequentially in space O star 3 to the n, and time O star 3 to the n, and poly n space. And when I count time, I'm assuming, let's say that evaluating f takes unit time. In the case we care about, evaluating f will take you poly time, right? Because you have to check whether or not this set is an independent set. Okay. So why is this true? When I say all, I mean for all s. Right? So if you think about this formula, I guess I erased it. The formula here was sum over s subset v, negative 1 to the v minus s of f hat of s to the k. Right? That was the value we had here. So I claim that you could, for example, compute this thing in 3 to the n time and poly space. So how would you do that? I'm sorry?
You don't have just 3 to the n subsets.
I mean, yeah, so not...
You can pasteurize at most 3 to the n.
yeah, so not... Right, so not even really recursion, but just kind of brute forcing it.
Yeah,
Right? So let's say you wanted all the hat values, right? The naive way to do it is you loop over all s and you compute, right? So let's look at hat, for example. F hat of s is the sum of all r subset of s of f of r. Right? So let's say that I wanted to compute, let's say we want, f hat of s for all s. And after we compute f hat of s for a particular s, we don't need to store it because we're going to keep it into a running sum that we're using to compute something else, right? We just want to compute the answer, throw it away, compute the answer for the next s, throw it away, etc. How much time does it take? Well, for each s, we take time proportional to the number of subsets of s, which is 2 to the size of s, right? So the time up to the star notation is the sum over all s's, sum over all r, subset of s, 2 to the size of r. And we already saw this before, right? What is this? This is equal to, well, actually, we want this for all s's. So the sum of all subset of v, 2 to the s, right? 2 to the s time because we have to loop over all r's which are in s. And we said, look, this is equal to the sum over all I from 1 to n of n choose I, that's the number of sets s there are, of 2 to the I. And we already saw last time that this is at most 3 to the n. Right? We talked about this last time. So it's 3 to the n time, and it's poly space, just by brute force doing it. So last time we mentioned that there's a dynamic programming algorithm for k-colorability, which took roughly 3 to the n time and 2 to the n space. But it turns out using inclusion-exclusion, you can do it in 3 to the n time and poly space. Okay. So what about a faster algorithm? So there's something called Yates' algorithm. And that gives you something like 2 to the n time n space. Okay. And I'll describe it for the zeta transform, and I'll actually prove that it works. And then I'll just mention what you would do for the Mobius inversion. It's very similar. Okay. So it's a dynamic programming algorithm. Usually I like to describe dynamic programming algorithms by just giving you the recurrence. I describe it as a recursive algorithm. And then you can turn it into dynamic programming using memoization, right? You remember the answers to things you saw. So let's come up with a nice recursive formulation that will get us all of the f hat of s values. Okay. So remember, we want f hat of s for all s. Let's define a function what I'll call g of I comma s as the sum over all r subset of s. And I'll say what this means very soon. Si equals ri times f of r. What's this s of I business? So s of I just means s intersect I plus 1 up to n. Let's say that all of these are subsets of 1 to n. Okay. So we want f hat of s. What's f hat of s in terms of g? Yeah, g and s, right? So note f hat of s is just g of n comma s, right? Why is that? Because when I is equal to n, the set from n plus 1 up to n is the empty set. So s of I is s intersect the empty set, which is the empty set. And the empty set always equals the empty set. So this is just always 1. So you have a sum over all r of f of r, which is exactly f hat of s. Okay. So we want g of ns. And we're going to come up with a recurrence that lets us compute g of ns. So first of all, the base case, g of, so let me claim it and then we'll prove it. I claim that g of is is equal to, first of all, the base case for me is I is 0. If I is 0, then this is everything. So s of I is just s. So this is just testing whether r equals s, which is only true when r equals s. So you get f of s if I is equal to 0. Otherwise, the recurrence that I'm going to claim is that this equals g of I minus 1s plus an indicator for I being an s times g of I minus 1 s minus I if I is bigger than 0. Okay. Okay. So just in terms of space and time, we're going to prove that this is actually correct. In terms of space and time, well, how many states are there in this memoized function? There are 2 to the n possibilities for s. There are n possibilities for I. So the space is like n times 2 to the n times the amount of space it takes to hold these sums. But these sums are, at most exponentially large, so you can write them down in at most n bits, O of n bits. I mean, it depends on what f is. I didn't say, f maps to some arbitrary ring. So the space is n times 2 to the n times the space to store a ring element. Okay. How about the time? Well, within each state, to compute the value for that state, you need to do at most a constant number of recursive calls, and then a constant number of arithmetic operations, right? So the time is proportional to the space. Okay. So you can compute all of this, and for all s, you can compute g of ns in O star of 2 to the n time and space. So now let's prove that it's correct. Prove that it satisfies this recurrence, I mean. So let's write gi of s in a different way. Let's just break up this sum into two pieces. So I can write that gi of s. Let me give myself some more space. So I can say, look, gi of s is equal to the sum over R subset of S such that I is in R of Si equals Ri times f of R plus the sum over R subset S such that I is not in R. Si equals Ri times f of R. Okay. So now let me prove to you that this actually satisfies this recurrence. So case one is that I is not an S. If I is not an S, and R is in S, is contained in S, then certainly I is not an R. In which case, the first sum completely disappears, because it's the empty sum. There are no such R's. Okay. But if I is not an S, well, Si minus 1 will be the same thing as Si. And I is not an R either, so Ri is also the same as Ri minus 1. So this implies first sum is 0. It vanishes. It's the empty sum. And the second sum is a sum over R contained in S such that Si minus 1 equals Ri minus 1 f of R, which is just g of I minus 1s. And this term didn't appear because I is not an S. So that's great. Case 2, let me maybe give myself some space, is that I is in S. Okay, so if I is in S, then if I is also in R, that means that Si minus 1 will equal Ri minus 1. Because both of them, both S and R contain I. So if I is in S, then the first sum equals the sum over all R subset S such that Si minus 1 equals Ri minus 1 times f of R. Okay. Which again is going to give us, where'd it go? It's going to give us this term, the gi minus 1s. And then let's look at the second sum. So in the second sum, we want to sum over all R's that don't contain I such that it agrees with S from I plus 1 onward. Okay. So that means that it agrees with S minus I from I onward. In the second sum, we want R which agrees with S from I onward, which implies that it agrees with S minus I from I onward. So what is that? That's the sum over all R subset S of S minus I equals R minus 1 equals Ri minus 1 times f of R. And this, remember, we're in the second case where I is an S. So for this term to appear, I has to be an S. And then we get exactly G of I minus 1, S minus I. So that's it. Okay. So summary, we can figure out, we can decide K colorability in roughly 2 to the n time up to poly n factors. Questions? And I should mention maybe some references if you want to see more on this. Can solve other problems using this technique. I only gave you one example. So for example, Min Steiner tree, find all K colorable induced subgraphs. And there are a bunch. Maybe so I'll give you some references. So you can look at, for example, Husfeldt has a survey article. I think it's called, actually I have a copy with me, An Invitation to Algorithmic Uses of Inclusion-Exclusion. Okay, so he's inviting you. It's an iCalc 2011. It's also on the archive. And there are several other, you can find more references in that paper. Yeah.
Like the algorithm you presented,
Yeah.
as byproduct computes f for each for all subsets. So
Yeah.
it already finds all K correlated to induced subgraphs, right?
Let me think for a second. Oh, right. So I said that this function g, I said that g of v is, what did I say? I said that g of v is bigger than 0 if and only if it's K colorable.
I would say,
Right? That was our final, it's erased now, but at some point, oh, this is a different g. I defined this function g, which said g of s is the number of choices of K independent, K non-empty independent sets that are all contained in S. And then we just wanted to check that, or whose union is exactly S, actually. And we wanted to check that G of V is strictly bigger than 0.
but once you
Oh, you're saying you
say
say,
transfer,
right.
you have value of g's for all subsets.
Yeah, that's actually, that is actually true. That's actually true, yeah. So let me think about what's going on there. Yeah, so what you said makes sense, yeah. So yeah, okay. But there are other problems that have nothing to do with coloring too, which you can solve. Okay. So before I switch to the next topic, one thing I should point out is, the first question that might come to your mind when you see this algorithm is, well, maybe I don't actually want to just know if it's K colorable. I want to actually find a K coloring, right? So at the end of the day, I evaluate this formula, I get something positive, I know there's a K coloring. How do I actually then find a K coloring? It turns out that you can do it in roughly the same algorithm, and roughly the same running time. So, for example, there's a reduction in the Bjorklund, Husfeldt, Fox 06 shows can also find k coloring. And O star 2 to the n. Time and space. It's actually very short. It's maybe a couple paragraphs. I'm not going to cover it in class just because I'm running low on time. But if you want, you can go. The paper's on archive. Check it out. I mean, it's a black box reduction. They're saying like if you can compute the chromatic number of a graph in 2 to the n time, then just black box that implies that you can actually find a k coloring in roughly the same time. It's not specific to their algorithm. So in the last, I guess, class and a half, I'm going to talk about something totally different. So before I do that, namely streaming and sketching, are there any questions?
You mentioned you were going to show like some version of this where it uses the Mobius version instead of the Zeta.
Oh, right. So, I mean, that formula I had, right? So the formula, remember we had G is k colorable. If and only if. And then I said this sum R subset of, what was this thing? So it's S subset of V, -1 to the V minus S, F hat of S to the K is bigger than 0. Right, so remember we had this was our algorithm. Our algorithm is just going to compute this thing, okay, and check that it's positive. So, I mean, the reason I said I was going to talk about zeta transforms and Mobius inversion, but this is exactly the Mobius inversion of the zeta transform. So, I told you about those two transforms to explain where this formula is coming from. Yeah. And then so this Yates algorithm. Oh, and I didn't mention how to actually compute Mobius inversion, right? I just mentioned how to compute the zeta transform, but maybe I'll leave that as an exercise. So there's almost an identical way to compute the Mobius inversion using a similar kind of dynamic program. Okay. Maybe I'll put that in the notes, or until then you can try and think about it as an exercise. Any other questions? Okay, so final topic. And so there are many kind of advanced algorithms classes that maybe spend more than a lecture and a half on this topic, but we have a whole class on this topic at Harvard. It will be offered next fall, namely algorithms for big data. It's not just on this topic, but this is one of the topics that we spend a lot of time on. So I didn't want to kind of reduplicate things that are in another class by too much, just in case you have taken it or will take it in the future. But sketching and streaming. And I'll also try to, next lecture I'll mention an algorithm that's connected to something we've seen already that can be used to speed up something we've seen already, actually. Okay, so what's the idea? So first, we'll cover streaming. Okay, and what is streaming? Streaming is it's really just data structures, small space data structures. Okay. So I'm going to look at a particular model. So we have some high-dimensional vector x say an Rn, or maybe high dimensional matrix, capital X. Today we're just going to look at a vector problem. And we want, just like data structures, we want to support updates to X and also queries about X. So what kinds of updates and queries do we want to support? Well, I'm going to talk about one kind of update that we're going to look at. So there's something called the turnstile model. This term was due to Muthukrishnan. Maybe in 05, but I'll look that up. And the idea is each update I is a pair. It's an index I as well as an amount V, causes the change xi gets incremented by V. Okay. And also at the beginning of the stream, let's say X starts off as the 0 vector. So for example, maybe n is the number of IP addresses that exist, so 2 to the 32 or 2 to the 128 in IPv6. And some algorithm is sitting in a router, and it's maintaining X, where xi is the number of packets that were sent to IP address I. Okay? So every time you see a packet, you can interpret that as an update. You look at where the packet is going to. It's going to some IP address I. That can be seen as an update I, 1. Right? There's one more packet going to that IP address. And then at the end of the day, you want to compute some query about X. So example queries, maybe you want to know, what is xi for some I? Or maybe you want to know what is the support size of X, right? How many IP addresses receive traffic since the beginning of the stream? Or how many packets did this IP address receive? Okay. And maybe I'll mention there's always the solution of either remembering X or the whole stream. So either, N or M space, where this thing here is the stream length. So the goal usually in streaming algorithms is to come up with an algorithm that uses much less space than the trivial solution. Right? You don't want to remember the whole vector, and you also don't want to remember the whole stream. So one goal. Use very little space. right? So you imagine you're seeing all the traffic going through your router. You're using IPv6. You don't want to use 2 to the 128 space. You don't have 2 to the 128 space. You also don't remember every packet that you've ever seen. Okay. So let's look at an example. Let's say there's only one query that's allowed, which is the support size. And for historical reasons, I'm going to denote this by F0. Okay. And also, all updates IV have, let's say, V being 1. In general, you might allow negative updates as well. But for us, we're gonna assume that this is the query and all updates have V equals 1. So really, it's how many distinct IP addresses did my router receive traffic today or something. Okay, that's the thing we want to know. Questions about this example problem before I say some more things about it? All right, so to be more precise, you can use exactly n bits of space to solve this problem. You just remember a bit string where the ith bit is 1 if you've ever seen IP address I. Or you could use m times log n bits of space where the stream length is m, remember. And what is a stream element? It's an index I, which takes log n bits. So to remember all of them takes m log n. So we want to do much better than that. Unfortunately, claim any deterministic algorithm for F0 requires, let's say, omega min nm bits of space. So unfortunately, we can't solve the problem much more efficiently. Let's prove this. And this I think was first observed in a paper of Alone, Matias, and Segedi. I know the conference version was 96, but I believe the journal version was in 99. So let's prove that. So it's going to be via an encoding argument. What do I mean by that? I mean, if we could actually solve this problem in less than linear space, we're going to be able to encode. So suppose I want to design a compression algorithm. Okay, what should this compression algorithm do? It takes as input an n-bit string, and it outputs some compression of it. What's a compression of it? It's just some mapping that can be inverted. Okay, it's some injection. So our compressed version, let's say we're compressing it into another string. Okay, so if I want a compression of all n-bit strings into some other bits, into say t-bit strings, how big does t have to be to ensure that this is possible? At least n, right? Just by the pigeonhole principle. I mean, or you can't have an injection into a smaller set. So that's what. So suppose, let me write down what I mean. Suppose we had a space S algorithm, streaming algorithm. We will show how to then design a compression algorithm mapping n-bit strings to s-bit strings. Which implies, as you said, s has to be n. Compression algorithm is an injection. So you can't have such an injection unless s is at least n. And the streams that are going to arise in this proof will have m being roughly n as well. So in this example, m and n are roughly the same thing. So let's design such a compression algorithm. So let's say Alice receives some x, which is in 0, 1 to the n, and wants to compress it. Using our F0 algorithm, A. So what does she do? Well, I mean, the A takes as input streams. So she's going to create an artificial stream, feed that to A, and then she's going to compress her string x as being the memory contents of A. Right? And since A uses s bits of memory, that's going to be an s-bit compression. So what's the stream that she's going to create? And we also have to show that it's an injection. And to do that, we'll give a decompression algorithm. So how does she encoding of x? How does she encode x? She creates a stream containing the set I such that xi is 1. Runs A on it, and then she outputs the memory contents of A. So now we have to show that this compression allows for decoding. So now Bob gets this compression, and he wants to decode. So what do you do? How do you decode and figure out what x was based on this compression? Yeah, exactly. Try adding more bits and see if the support size changes. Right? So we're given mem contents of A. And we'll continue running A starting with this state. Okay, so what do? Here's the algorithm. Let's let Z be query. Okay, A dot query. So that's the number of distinct elements in the stream, starting off from where Alice left off, basically the number of 1 bits in X. And then for I being 1 to n, we'll insert I in the stream. And then we'll check if A dot query now has gone up, that means that, sorry, no, not if it hasn't gone up. If A dot query hasn't gone up, it means that the ith bit was already 1, right? Which means that xi is 1. Otherwise, if it did increase, Otherwise, xi is 0. And then now we'll set z to be the new value. That's the decoding algorithm. Questions? So, great. So we can't do it with a deterministic exact algorithm. So let's look at deterministic exact f0. We just showed that that's impossible. How about deterministic approximate? How about randomized exact? And how about randomized approximate? What do I mean by these? Here I mean it's a deterministic algorithm. It always is correct. Okay? And it doesn't give us the support size, but it gives us a value which is going to be within 1% of the support size. Like guaranteed. What do I mean here? I mean we have a randomized algorithm which, with 99% probability, will give us the support size. With the other 1% probability, it might output some junk. Okay? So the question is that possible? And then this is like the most relaxed version. It's a randomized algorithm with 99% probability. It'll give us an answer that's within 1% of the true answer. And then with 1% probability, it might give us junk. Okay. So it turns out that I'm not going to prove it here. Both of these are also impossible. You can prove, also via encoding arguments actually, that these things are also impossible. All of these are due to the paper AMS. And it turns out that, yes, this is possible. And when I say possible, I mean possible in sublinear space. It's always possible by remembering everything. And this is due to Flageolet and Martin in JCSS 85. Okay. Yeah. Yeah, let's say you want any constant, like two approximation. Yeah, it's impossible. Yeah.
Can we get any kind of bound on the jump that it might spit out?
You mean in the randomized? No, it's just going to be, it's like this Monte Carlo kind of algorithm, right? So there's, in general, when you talk about randomized algorithms, there's this Las Vegas Monte Carlo. Las Vegas means it's always right, but the running time or the space or something is expected. And Monte Carlo means the efficiency is always guaranteed, but the correctness is randomized. So this is this Monte Carlo flavor, and yeah, we don't have a guarantee. When it's wrong that 1% of the time, it's just, it could do anything. You can decrease that 1% to be as small as you'd like. You can make your failure probability be delta, let's say for this problem, but you would pay in your space by paying some log 1 over delta factor. Okay, so just let me wrap up by showing you kind of why this is even possible. Okay, why is it possible to beat, or give you some intuition for why it's possible to beat linear space if you're allowed randomization and approximation. So remember, what's our goal now? Is to develop a randomized algorithm A such that for all for all streams S, the probability over the randomness in the algorithm that, let's say, the output of A on stream S minus F0 is bigger than, let's say, epsilon times F0 should be at most, let's say, a third. You can make this third be as small as you'd like, make it be delta. You'd pay something in your efficiency. So let's look at an idealized randomized algorithm. This is Flageolet-Martin. So why is it idealized? The next thing we're going to write is going to be idealized. So let's say we have a totally random hash function, which maps. From now on, I'm just going to call this thing bracket n. It maps our universe, our coordinates of this vector x, into the continuous interval from 0 to 1. So each index of x gets assigned a totally random fraction between 0 and 1 by this hash function. Uniform. Okay. Uniform value. So already this is a little problematic. We can't actually store, the point is to use sublinear space. And if I'm telling you I'm using a totally random hash function that has n different possible inputs, we have to store these n random numbers. That's already n space. Furthermore, these are real numbers, and our computer can't store real numbers, right? It has finite precision. So that's another catch. So it turns out that you can discretize, you can make an algorithm like the one I'm going to tell you work by discretizing this. So the precision you need is not that bad. Okay, you can discretize this into fractions whose denominator is, say, poly n. So you just need to work with numbers that take log n bits of precision. And another thing is, the fact that you need n random numbers, that would take you n space to store this hash function. But remember earlier in the course we talked about pairwise independence and other kind of limited randomness hash functions. You can use those kinds of things to in place of what I'm going to tell you as well. Okay, so I'm not going to talk about that here, but you can get away with a reasonable hash function that doesn't take that much space to store. Okay, so the idea that makes Flageolet-Martin work is the following. So here's the algorithm. Let z be the min over all I in the stream of h of I. The number z can be stored just using one number. Z is one number, right? So this is like one unit of memory if we can store real numbers. Right? Every time you see an I, you hash it, and then you set your current value to be the min of what it was before, and then you hash. And then when you ask for a query to answer a query for the number of distinct elements, or the number of the support size, we output 1 over z minus 1. If you want to, so here if I put this epsilon here. So if you want an epsilon in your guarantee, what you'd actually do is you'd pick h1 up to hr independently, where r is going to be something like 1 over epsilon squared. Okay. So you pick r totally random hash functions, 1 over epsilon squared totally random hash functions. And then we're going to let z, let's say zj, be the min over I in the stream of hji. Basically, run this algorithm r times in parallel with different random hash functions in each iteration. So now you're only remembering r units of memory as opposed to one number of memory. And then what do you output? You output 1 over, let's call it z bar minus 1, where z bar is just the average of all the zi's, or zij's. 1 over r sum j from 1 to r of zj. And the idea is this averaging will decrease the variance, so that if you average enough of them, you'll be within a multiplicative of 1 plus epsilon as opposed to constant error. So I haven't proven anything, but are there any questions about the algorithm? What the algorithm does? No? Okay. So the basic idea is, look, let's look at this hash function h. So we have this continuous interval from 0 to 1. And we're hashing these f0 items. F0 is the support size. We're hashing these f0 items into this interval. So kind of what do we expect to happen? We roughly expect them to be roughly evenly spaced, where the gaps will be roughly 1 over f0 plus 1. And the smallest of the hash values, we expect the smallest of the hash values, an expectation, right? That should be 1 over f0 plus 1. Okay. If you want to formally prove that, you can say, look, the expectation of z is the integral from 0 to 1, the probability that z is bigger than x dx. And then you can compute this and get what I said. Okay. Right. So maybe the easiest way to do this is to say this is 1 minus the probability that z is at most x. And then this thing here is the probability that for all I in the stream, h of I is at most x. Right? And since the h values are independent, this is equal to the product over I in the stream, the probability that hi is at most x. And this thing here is just x. Right, so z is the min. Oh, right. Very good point. You can't do math. So, good. So for the min to be bigger than x, this means that this is the probability that for all I, h of I is bigger than x. Okay, in the stream. And this is just equal to 1 minus x to the f0. Okay, good. And then you can integrate that over x, and you get what I said, and evaluate it, and you'll get what I said. Okay. You can also show you can also show that the expectation of z squared, again by a similar kind of integral, is equal to 2 over f0 plus 1, f0 plus 2. I'm not going to do it for you, but you can show it. And remember that we have Chebyshev's inequality. The probability that z minus the expectation of z is bigger than, say, epsilon times the expectation of z. Is at most the variance over epsilon squared times the expectation of z squared. And this is at most the expectation of z squared over epsilon squared times the expectation of z squared. Okay. So you can do this kind of thing to analyze and say, look, there's a decent chance that z is actually close to its expectation, meaning it's close to 1 over f0 plus 1, meaning that if you invert it and subtract 1, you'll get something pretty close to f0. That's the basic idea. And the second algorithm here, where we averaged a bunch of copies before inverting it, what's the point of that? The point of that is, look, so each one of those copies has the same expectation. So when we average it, the expectation of the average is the same thing. But when you average it, the variance goes down by a factor of the number of things you averaged. So if you average r things, the variance goes down by a factor of r. So if you set r to be 1 over epsilon squared, the variance goes down by a factor of 1 over epsilon squared, which is just enough to kill this epsilon squared here and make this thing still small. Okay, so that's basically how this works. And yeah, I guess class is over. Any questions about this algorithm? Or, I mean, it's idealized, I already mentioned, but any other questions? Question? Or?
No, I was just thinking about, so this is just if you want to be able to query only the support size.
Yeah.
So like how much more complicated is it going to be if you want to actually be able to query individual?
Oh, you want to know xi?
Or something more specific than just the size of the entire support.
So yeah, so you said something more specific than the size of the entire support. So one, I don't know if this is what you mean, if what you mean, but so here it's funny in that there's only one kind of query. Oftentimes when we solve data structural problems, there are lots of different possible queries. You could look at other problems too, like a query also gives you an index I, and you have to give xi. So just like we had all these impossibility results for support size, you can prove such things for other things as well. So for example, that problem, given I output xi, there's no deterministic exact algorithm. There's no randomized exact algorithm. But actually, there is a deterministic approximate one. And there is also a randomized approximate one, which is slightly more efficient. What does approximate there mean? It means I'm not going to output xi, but I'm going to output, say, xi plus or minus some error term. And that error term is allowed to be, say, epsilon times some norm of x, maybe the L1 norm or something. So for that kind of relaxation of the problem, you can also get small space algorithms. And there you have lots of different possible queries. You have n possible queries.
So why can't that be used to get a deterministic approximation for this support size?
Well, so you get this for every single I, right? Yeah. So in particular, if xi is 0, the query algorithm might tell you that xi is epsilon times the L1 norm. Right? So you don't know which ones are actually 0 and which ones are maybe close to 0.
What if they're discrete?
If what's discrete?
The value. So like what if xi are integers?
Oh, I mean, even if they're integers, right? So let's say, I mean, epsilon might be a tenth or something, and the L1 norm might be divisible by 10. So, I mean, this thing will still be, this might still be an integer, and you wouldn't know whether or not it's, whether or not it's 0 or non-zero, whether xi is 0 or non-zero. I don't know, does that answer what your worry is? Or?
Well, I mean, there you're allowed to choose epsilon as small as
Yeah, but then your space will increase as a function of epsilon. So, for example, in the deterministic algorithms, your space will be like 1 over epsilon squared. In the randomized algorithms, you can get space 1 over epsilon, up to some extra, maybe log 1 over delta, et cetera. Okay, I think we're definitely out of time, so I guess I will see you Tuesday. Happy Thanksgiving.